You can start, Vicent, please.
Okay.
Okay.
Well, welcome everybody to this edition of European Non-Associative Algebra Seminar. It is a pleasure to introduce you our today's speaker, Agata Pilitowska from the Warsaw University of Technology. She's going to speak about diagonals of solutions of the Yang-Baxter equation. So, Agata, please, you can start when you want.
Thank you very much. First of all, I would like to thank you for the invitation and the possibility to present my results at the seminar. As Vincent said, I will talk about diagonals of solutions of the Yang-Baxter equation. The main aim of this talk is to show you to define these mappings and show that these mappings may carry deep information about the structure of solutions. This is the joint work with Premysl Jedlicka from Czech University of Life Sciences. At the beginning, I would like to recall shortly the definition of the Yang-Baxter equation. In more generality, this equation, which is present in physics especially, is defined on the vector space, some linear mapping defined on the vector tensor product of some given vector space into the same vector space is such special that this mapping satisfies such relationship. This equation, as I said, is important for physics because, for example, it describes how waves behave in shallow water, may describe the interaction of subatomic particles. It is present also in mathematical theory of nodes or in string theory and in many others. It was formulated, this equation was started to investigate and formulate by Yang and Baxter independently in the end of the 60s and beginning of the 70s. But of course, to find all solutions of this equation is very difficult and even impossible. So in the beginning of 90s, Greenfeld proposed some simplification of such equation, and he proposed to define it not on the whole vector space, but only on the basis of this vector space. So at the beginning, we can take a set and two binary mappings, say sigma and tau, and to consider some mapping which is this is extension of the when we define define the mapping of the tensor product of any two elements from the set X in the following way, as a tensor product of the image of the first and the second binary operation. And when we assume that this mapping extends to the solution of the previously defined equation in the general form. This follows that this new solution must satisfy a special braid relation, which we can translate in the following way. So instead of the tensor product of mappings, we have only mappings defined on the Cartesian products of these mappings. Of course, on the left and right-hand side of this equation, we have a mapping defined on 3 variables. So we can read this description, this Cartesian product of 2 mappings, which one is unary and the second one is binary operation, will be translated in this way. So if we will consider a solution, so some set defined on the product of set X into the same product as a pair of 2 binary mappings, so we can think about the image of this mapping as a pair defined independently on each coordinate. When we fix in the first mapping the one, say, first variable, say, so we obtain unary operation, which we can think about this as a the same we can make with the second binary operation. So we assume that we fix the second coordinate, so we also obtain the unary operation. In this case, this braid relation, which we obtain using the assumption about the extension to the general equation, implies a system of 3 identities which are formulated in the language of these of the family of these 2 unary, the 2 families of unary operations, sigma and tau. It is not so much important for my talk, but I would like to show you how we can define such equation. Very simple and basic example of this simplification. We will say this simplification, that this theoretical set solution of the Yang-Baxter equation, is given by so-called Lubashenko solution. If we take any 2 commuting mappings, and when we assume that each unary operation for any x, sigma x, are the first mapping, and the second family of unary operations is defined only by this second mapping, we obtain a solution. Another more interesting is it may be defined on any group. So as a result of the first unary operation, we can take this expression calculated in this given group, and as a second family of tau operations, the mapping defined the result of this, the image of this mapping defined in this way. So it is possible to check that the system of 3 equations for this unary operation are satisfied, and so we obtain on the set G an example of a solution. Okay, but any set theoretical solution may be also described in the language of algebras. In this way, we obtain algebraic structure with 2 binary operations defined in the following. If we take a solution which is defined by 2 binary operations, sigma and tau, or the 2 families of unary operations, as we can define 2 binary operation x circle y defined as a result of this unary operation sigma s of u, and the second operation bullet, defined the same way by using operations tau. When we translate this relationship defined, which we obtain from the braid relation, into the language of these two binary operations, we obtain three identities which must be satisfied in our algebra. So we can say this well-known result that there is one-to-one correspondence between such algebras, such in this sense that they satisfy these three conditions, and any solution of Yang-Baxter equation. Okay. Among of all solutions, we can distinguish two very important classes. I would like to focus on two of the so-called bijections solutions, and a little later I will say about non-degenerated one. Bijective solutions are those for which the mapping R is invertible. In particular, if it is self-inverse, so the composition with R is identity, we will say that our solution is involutive. It is well-known fact that if we have the inverse of the mapping R, so the set X with this inverse is also a solution, and we will denote it by R with hat. Let us look for some examples. If we take Lubashenko solution, and when we additionally assume that both mappings F and G are not only commuting but are permutations of the set X, so we obtain bijective solution. And this new solution with the inverse operation of R are defined by the inverses of F and G. But of course, there are also non-bijective solutions. They are, for example, proposed by Svetka and Verwimp. They built this solution on the distributive lattice, and they take as a unary sigma operation the supremum of X and Y, and by the tau unary operations, the infimum of this pair. In this way, we obtain a solution by this solution is non-bijective. Okay, the second class of solution, which will be very important from my point of view and was very popular in many investigators, is so-called non-degenerate solution. We say that a solution is left non-degenerate if all sigma unary operations are bijections. Okay, similarly, we can define right non-degenerate solution when we assume that right tau operations are bijections. If both conditions are simultaneously satisfied, we say that our solution is non-degenerate. For example, Vadas which are always, for any group, are non-degenerate solutions. Lubashenko solution is, of course, non-degenerate if we assume that F and G are bijections. The solution which we can say are some kind of constant solutions. So for any unary operation sigma x, the result for any arguments is this the same x as in index of sigma, and the same is also true for the tau unary operations. And this solution is an example of degenerate solution. Of course, these operations are not bijections. Okay, such solutions are the counterpart in the algebraic structure, and not only one-sided non-degenerate solution, say left non-degenerate solution, may be fully described by so-called Q-cycle sets. Such algebraic structure was proposed by Verwimp, and it is, as previously for the whole solution, it is a set with two binary operations which satisfy the system of three equations, which, as you can guess, follows from the braid relation. Additionally, we assume that because we want to obtain the left non-degenerate solution, we assume that the mapping, the left translation by x with respect to the multiplication, dot multiplication, is invertible. So Verwimp proved that there is one-to-one correspondence between Q-cyclid set, in the sense as I defined on the previous slide, and the left non-degenerate solutions. If we take any left non-degenerate solution and we define the operation dot at the inverse of sigma x unary operation and the colon operation in the following way. So we obtain with these two operations a Q-cycle set. On the other side, if we take a Q-cycle set, we can define, so assume that we introduce the notion for the dot operation. We denote this result of multiplication, but dot x by y as a sigma x of y. And when we introduce the unary operation lambda with index s as an inverse of this operation, so in fact, if we have a Q-cycle set, we know that this operation multiplication by dot is the inverse operation, so that is well defined. And as a second family, we take this expression. So we obtain a left non-degenerate solution. Okay. But if we have fully non-degenerate, so left and right non-degenerate solution, the counterpart in the algebraic structure of such solution is given by so-called BIRAC. We can define this algebraic structure as an algebra with four binary operations. The circle and bullet are exactly the same as for the general solution, so they must satisfy the system of these three identities. And additionally, because in this case, both left translations using sigma and right translations using tau are invertible by assumption, we obtain that we can define additionally two binary operations, which are some kind of inverses of this circle and bullet. And in fact, these the set X together with the operation circle with this, say, division of the inverse of this operation is a left quasi-group, which means that such identity must be satisfied in this algebra. And the second part of binary operations forms a right quasi-group in this sense, as is it written here. So it is also very well-known fact that there is one-to-one correspondence between non-degenerate solutions of Yang-Baxter equation, of course in the theoretical sense, and Biracs. So as an example, we can take our Lubashenko Birac. In this case, we additionally add two operations, the inverse of f and inverse of g, because we at first assume that they are invertible. And if these operations are commuting, we obtain a Birac. If we consider a Wada switch, so the Birac, which is a counterpart of this solution, is defined by two additional operations given by left and right division, we can say. So we obtain that circle, and this division with respect to the circle is left quasi-group, and with the second pair of operation we obtain the right quasi-group. Okay, so we know what is the set theoretical solution of Yang-Baxter equation, and we know few different algebraic structure which may describe these solutions. Okay, so we are in the point when I can define the main topic of my talk, diagonal of a solution. If we take a non-degenerate solution, we can define two unary operations, two unary mappings, U and T, in the following way. The image of U is the inverse of the image of X by U is the inverse of sigma X of X, and dually for the second diagonal T. Of course, if we only assume that our solution is only left non-degenerate, we are able to define only one, the first one of this mapping, and dually, if it is right non-degenerate, we can define the second one. And we will call such kind of solution, such kind of mappings, diagonals of our solution. And as I said at the beginning, many very important properties of a solution may be expressed by properties of these functions. I will show you two different problems which may be expressed using properties of diagonals of a solution. The first question appeared when these two operations mappings are bijections. It was known that in the case of involutive solutions, so when the operation R is self-invertible, they are, and additionally, the inverses are closely related with this diagonal. So the inverse of U is the operation T and vice versa. It is also true not only for involutive solutions. It was also known that it is true for so-called for such solutions which originate from special algebraic structures called skew braces. Skew braces are were defined by ring theorists and investigated by them. This is another algebraic structure which is closely related with solutions. But in general, it is not true. Even for Lubashenko solution, if we take such pair of mappings F and G, that F is not equal to the inverse of G, so of course the mapping U, it is easily checked, is the inverse of F, and the inverse of T is G. So this relationship between them is not true in this very simple example. Also, if we take non-degenerate solution in at least one of these two binary operations, sigma or tau, is an identity mapping. But we assume that tau is such that at least one unary operation tau x is not an identity. So for this solution, diagonal mapping is identity, diagonal mapping U is identity, but the inverse of T is exactly on the argument x. X is exactly the image of tau x of x. So if we assume that at least one is not equal to x, we obtain... Sorry? Sorry, I don't...
Sorry?
I can't hear you.
I think there was a problem.
Okay.
I think you can continue.
Okay, thank you. But if we have that for all x, the image of unary operations sigma x and tau x is equal exactly x, we will say that our solution is square-free. So it is not difficult to note that if our solution is non-degenerate, so if it is square-free, so diagonals are very trivial. They are both equal and equal to identity. Okay, so if our solution is not only non-degenerate, but also bijective, we can ask about the diagonals in this inverse solution. We know that with the inverse of R, we have a new solution. And of course, this solution is bijective. And additionally, if our solution is non-degenerate, so the inverse solution is non-degenerate also. So we are able to define diagonals for the inverse solution. Using definition that the inverse solution is such that when we compose R hat with R, we must obtain identity and vice versa. So using the relationship with which we obtain for the sigma x, tau x, sigma hat x, and tau hat x, we can calculate that the inverse of sigma hat with index x of y is expressed in the following way, and similarly for the inverse of tau hat. So the diagonals of the inverse solutions are as follows. The diagonal is, of course, the inverse of tau hat x of x. Using this relation, we obtain this result. So we immediately have that the diagonal, T diagonal of the inverse solution is sigma from the original solution with the index T of x diagonal from the originate solution of x. And similarly, we obtain the same result for the diagonal of the inverse, the second diagonal, U diagonal. This is defined as a tau with index U of x of x. Okay. For only one-sided non-degenerate solutions, Verwimp proved that if we take a left non-degenerate and additionally bijective solution, so the following conditions are equivalent. So our first question was when diagonals are bijections. So when we assume that our solution is left non-degenerate and bijective, we Verwimp proved that the diagonal is invertible exactly when the diagonal in the inverse solution is invertible, and if the solution is non-degenerate or the inverse solution is non-degenerate. Of course, in this case, because if only one diagonal is invertible, it is well defined because we assume that we have a left non-degenerate solution. So these the inverses of diagonals are related by this expression. So in general, for assumptions given by Verwimp, the inverse of U, diagonal U, is the diagonal or T in the inverse solution, and dually the inverse of the diagonal in inverse solution in the second diagonal in the solution. Okay, but still we didn't know what is in the general case. Okay, Verwimp and Jespers and Okniński showed that when we assume that our solution is finite, left non-degenerate and involutive, so in fact it is right non-degenerate. So it is in fact non-degenerate. Later on, Castelli, Catino, and Stefanelli proved that also for finite and left non-degenerate, but in more general case, all bijective solutions, the same result is also true. So all finite left non-degenerate bijective solutions are in fact non-degenerate. So in the light of these results, Verwimp proved that in any finite non-degenerate bijective solution, the diagonal mappings are invertible and the inverses are expressed by such formulas. Okay, but when we compare, okay, a little more than 1 year ago, we proved that we can forget about assumption about bijection of a solution, and we can also we also do not need assumption about finiteness of our solution. So it is enough to assume that the solution is a non-degenerate to obtain that both mappings, both diagonals U and T, are bijections. So we obtain the whole description about this, the behavior of these two mappings in non-degenerate solutions. Additionally, we showed that these two mappings commute always, and they are the inverses are described by the same formula as was presented by Verwimp. So we can say that in general, if we take a non-degenerate solution, finite or infinite, so always diagonals are invertible and inverses are given by diagonals of inverse solutions, but not so the inverse of this first diagonal is the second diagonal in the inverse solution. Okay. So the natural question arises, what is the relationship between bijective solutions and non-degenerate ones? Okay, let us once again consider our examples. If we take a Lubashenko solution with commuting bijections f and g, so as I presented previously, this solution is bijective and non-degenerate. If we take this some kind of constant solution, so we can show that it is bijective, but of course non-degenerate. Cedo and Verwimp solution, as we said, is non-bijective and degenerate. So there are bijective solutions which are not degenerate. We have the second example, but we didn't know, is there a non-degenerate solution which is not bijective? So we try to not only me and Przemek, but other researchers try to find the answer for this question. And because there were no such examples, so they concentrate for some weaker assumptions. They started to consider only left non-degenerate solutions. And Stanowski and Wojciechowski defined on the group a solution in this way that all sigma x are left translations by x with respect to the group operation. And the second family of unary operations are all equal, are all constant, equal to the neutral element in the group. So this solution is, of course, left non-degenerate, because in any group such operations are invertible, but it is not bijective. So we have such example, but only with the assumption of one-sided non-degenerate, only for left non-degenerate solutions. Cedo, Jespers, and Verwimp propose another example defined on the set of integers. This is the formula, exact formula. And it is possible to show that this is the solution, a solution, and it is an involutive solution. So in fact, it is a bijective solution, but it is also left non-degenerate, and but it is not right degenerate. Okay, so natural question is, are non-degenerate solutions of Yang-Baxter equation always bijective? Because there was no still any example of the full non-degenerate solution which are not bijective. This question was stated by Cedo, Jespers, and Verwimp. But when we compare our result about diagonals, as you remember, we need to show, we only need to show that diagonals are, okay, bijections. We only need to show that, we only need to assume that solution is non-degenerate. The first result was presented by Colazzo, Jespers, Antwerpen, and Verwimp, and they showed that the answer is positive in the case of finite solutions. Additionally, they showed also that for any non-degenerate solution, diagonals mappings are always injective, and the solution is bijective if and only if the diagonals are bijections. So when you compare our result, that to show that our that diagonals are bijections, we need only assumption about non-degenerativity of our solution. We obtain immediately the affirmative answer for this problem. So just from this result, we know that assumption about if we assume that our solution is non-degenerate, so in consequence, each such solution is also bijective. So it means that the inverse solution exists. Okay, but there is some family, some class of solutions in which only one-sided non-degenerate, only assumption about the, for example, left non-degenerativity or only right non-degenerativity is enough to show that the one of diagonals are also invertible. One of such class of solutions are so-called two-permutational solutions. This class may be defined by a system of four identities. You can see that this is the sense of these equations are given by by taking arbitrary variables in, I can say, in the second level of the indices. So it doesn't matter if we take X or Y, the result will be the same. And it is possible to prove that for any non-degenerate, any non-degenerate solution, in two-permutational solution, the inverse of diagonals is expressed only in the language of, for the first one by the sigma, and for the second diagonals by operations tau. Of course, if we assume that our solution is, for example, only left non-degenerate, so we obtain that the left diagonal is invertible, and the same is for right non-degenerate solution. But diagonals are may have also some additional strong property. For example, in the case of these two permutational and non-degenerate solutions, we obtain that diagonals in these solutions are automorphisms of the solution. Recall, automorphism of a solution is a bijection, which, shortly speaking, preserve this solution. So we can say that the composition, any diagonal with T or U or T with any sigma x is the same as sigma with index of the image of this variable over the diagonal U composed with U, and the same for tau and the same for T diagonals. This is a property which is not true for any solution. This is an example built on a 5-element solution. In this case, this is non-degenerate because you can see all unary operations, sigma and tau, are defined by permutations of this 5-element set. You can check that, say, first diagonal is the transposition to 3, but this condition, which I wrote here, is not satisfied. Diagonals are also appeared very useful in the description of these two permutational solutions. Some years ago, we showed that each non-degenerate two permutational solution happen into two classes of solutions: two reductive ones, which are defined by this system of equations, and strictly two permutational. This identity is a simpler form of the definition of two permutational. These two reductive solutions are very combinatorial.
May I ask something? Hello.
Yes, yes.
I have a question. Can you go back to the previous slide?
Okay.
Yeah, no,
This
next
one?
slide. This is, if I understand correctly, this is what we call cyclic condition, already more than 10 years.
Yes, Tatiana, this name.
It, if I understand correctly, this is left cyclic condition and the other is right cyclic condition, and this is not only used, these solutions with these conditions are studied already 15 years.
Yes, because this is a condition which even went from the quantum theory or Rock's theory. This is well-known condition. Because it by this property, the wide class of different binary algebras are characterized.
To this. Every square free solution has this property, for example. Every square free
I
solution
no
satisfies
no no
the
no.
cyclic condition.
I'm afraid that not every square free solution has this property.
Unless I don't understand the two reductive definition.
Uh,
Anyway, sorry.
Because it is not true. It is even two permutational solutions, which are which may be.
No. My question is, this in the small pink frame that is called two reductive solution? This condition is this something different from what we call cyclic condition?
Maybe I didn't remember exactly what does it mean cyclic
when
condition.
When you left on the when you act on the left upon upon A with Z or with Z to the power X, it doesn't matter. It is the same result for every X and every Z. This is the so-called left cyclic condition. But now I don't want to take your time because you have worked with this. So this is only satisfied for square free solutions both.
Okay, so probably it is not the same. Because this condition is not satisfied for all square free solutions.
Okay. Maybe I don't understand this condition because I see it first time, but it reminds me something very well known. Okay, go ahead.
Thank you.
So to call things with different names but the same property does not contribute to.
Yes, of course. Okay, thank you. I can go to the. As I said, we can divide all two permutational solutions into two classes. These two reductive ones and strictly two permutational, which are not two reductive ones. And because, as I said previously, any non-degenerate solution is maybe described as a biject. So we have two separate left and right quasi-groups. So we can adopt some methods which are familiar in this theory, and for these solutions we defined so-called isotopes of mappings. Shortly speaking, we have in this way that if we take any solution, we can define new family of unary operations by composition. Any unary operation with this, this is given solution. We can define a new family by the composition unary operation sigma with our diagonal operation, and the same for the second family tau. If our solution is two permutational, we obtain that this new structure with these new families of unary operations, our solution is two reductive and square free. And additionally, we know that for these two permutational solution, both diagonals are automorphisms of this solution. Additionally, these two diagonals are also automorphisms of this new two reductive square free solution. Okay. This is the first application of diagonals, and at the end I would like to show briefly how we can use diagonals to say something about the composability of solution. It turned out that such mappings are important criterion of decomposability. Recalling, if we defined a group by all translation unary operations tau and sigma, so we obtain so-called group of permutations of a solution. And if this group acts transitively on the set X, we say that our solution is indecomposable. So it has only one orbit, which means exactly what is written here. And Tatiana showed many years ago, he stated many years ago at conjecture that each finite involutive square free solution is decomposable. And this conjecture was proved by Verwimp, and he also proved that for infinite set it is not true. But Ramirez and Bendramin reformulated the Room's theorem in the following form, that each finite non-degenerate involutive solution for which the diagonal maps fixes all points of X is decomposable. And he uses these diagonals to improve this result. In particular, they showed that in non-degenerate involutive solutions of size n, if say the diagonal T is a cycle of length n, all such solutions are indecomposable. But if this cycle is of the length n minus 1, such solutions are decomposable. Later on, Campmore and Sastricus showed that exactly in the same kind of solutions, if the order of the permutation of the diagonal T and the cardinality of the solution are coprime, so this solution is also decomposable. So you can see that the role of these mappings are essential. Okay, this is the end of my talk. Here is some chosen references. Thank you very much for your attention. This is all.
Okay, thank you very much, Agata, for your very interesting talk. Are there any questions, comments? Well, I have a question about the results, because I mean, as you showed, the result. I mean, the diagonals play a very important role in the case of two multi-permutational solutions. Which are the restrictions in general for?
Vincent, I hear you very bad.
Now, can you listen? Can you listen better?
Yes, just now better.
Tatiana, what are you asking something?
I first of all want to apologize. I read it in a different way. Sorry, you're absolutely right. That this is another way to say the secondary track collapses in a point. And the second thing I want to say, thank you for the interesting talk.
Thank you.
Nice to see you.
See you.
Yes.
Yes, no, I'm just asking. I'm just asking about the general case of multi-permutational levels. Which are the restrictions, for example, for three multi-permutational case? I mean, have you thought about or?
You ask about this case, for example.
Yes, yes.
Okay. it is in more general situation, we can prove it that we can replace two permutationality by k permutationality. We can present the system of equations which describe this class of solutions. Comparing with results of Tatiana for involutive cases, this is some natural extension, but in the case of in the involutive case, we only needed one particular equation. Tatiana uses so-called notion of towers to describe it because the indices goes down very quickly.
I mean, so it is possible
because
to iterate this.
And you are right. Such kind of solutions are closely are in one-to-one in equivalence with multi-permutation solution of level k.
Okay.
And it is the same theorem as the same theorem is also true when we replace 2 by k. Okay. But the form of this inverse is with k. We have add more sigma in the index.
Okay. Yes, of course. Okay. Very nice. Are there any questions?
May I say one more comment?
Of course.
So when we have these two permutation solutions, if XR is split into any kind of R of sub-solutions, in fact, it is how they call strong twisted union of these sub-solutions always.
Okay.
Just this is the condition for being strong twisted union when the left action does not depend, but doesn't matter. This is just additional comment. It is okay. Everything is fine.
Yes. Thank you.
More comments? So if not, let's thank again Agata for this very interesting and illustrative talk.
Thank you very much.
And I think that we can end this edition, and next edition I think is in maybe Jovi, you are more about it. I think is on the next talk will be the 30th of June, no? By
Yes.
Vincenzo Nardozza. So